Okay, there we go. This is John Gonder, and I am presenting in this video what I think is good background and basics for protocol analysis. And the reason I'm doing this is because in trying to identify resources for my students to look at to get some background about what are these things, where do they come from, and what do they mean, and putting it in some kind of context so that it can help in understanding protocol analysis. I'm just unsatisfied with what I was seeing. And this actually is another reason why I'm always in all my classes telling people you must know everything that is included in the A+ learning. Whether you take the certification exam or not, it is foundational that you understand what are these things and how do they work, because that's just basic for everything else to be making sense. Well, we already know the OSI model, right? Layer 1 is a physical layer on up through layer 7, the application layer, but what is it that's actually going on? Inside these things are transistors, which form the basis for everything. They're either on or they're off, and they represent a 1 or a 0, and that combination of ones and zeros is what everything devolves down to. And when we have an idea of how that is actually all working, then we can start to make sense of things when we see them working and understand where things go wrong when they don't. This is how I learned about all this stuff way back in the day, by actually building an 8-bit central processing unit, CPU, just right there with wires and resistors and LEDs. And actually this picture is a little bit more sophisticated because it has this LED set here down in the right-hand corner. And we actually had individual little LEDs there. But that's how you, and then actually entering one piece of information at a time, entering one bit at a time to form a byte, which then goes into and watching it step through each of the different parts of a CPU and then come out with an answer on the other end. Gives you a mental picture of how these things work. And I don't understand how people these days can really get that kind of understanding, that foundational knowledge. But that's what I'm hoping to convey a little bit of here, because everything that's going on here, this recording itself is taking an analog signal and analyzing it and turning it into a stream of ones and zeros that represent, when it comes out the other end, what it is that went inside. There's an encoding to the signal, whatever that signal happens to be. If it's an electrical signal on a telegraph, whether it is a light flash that's either short or long, Morse code, which you may know, SOS, save our ship, SOS, dit 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 da 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 dit dit dit. Those two things, like it's either a dit or it's a da, and a pattern of that represents something, and that's what we're going to take a look at in a second here. We're very used to thinking in terms of powers of 10. This is something we learned in 5th grade and we don't even think about anymore. If I see this number 1267, even as I say that, I'm not thinking about what it is that I'm interpreting to get the meaning of that. That I already know this is 7 in 1's place. The power of 10. 10 to the 0 is a 1. 10 to the first power is a 10. And in this position of a number, that means I've got 6 tens. In this position of a number, that means I've got 2 100s, or 10 to the second power. 10 to the third power, I have 1 1000. So I have 1,000, 2 hundreds, 6 tens, and 7 ones. And that's how I interpret that encoding. Well, our transistors are on or off, right? It's a 1 or a 0. It's a 1. It's a 0. It's a 0. It's a 1. How do we make a plan to interpret that? Well, we put 8 of those together, typically, and we look at it in terms of the powers of 2. Starting from the right-hand side, the first bit, 1 or a 0, represents 2 to the 0 power. It's either a 1 or it's a 0. Second, 2 to the 1. It's a 2. It's either a 2 or it's a 0. Third, 2 to the squared. It's either a 4 or it's a 0. Next, it's either an 8 or a 0, or a 16 or a 0, or 32, 64, 128 in these 8 bits can represent, if they're all 1s, we add it up. I got a 128 plus a 64 plus 192, well, plus a 32 plus a 16 plus an 8, a 4, and a 2, and a 1, and it makes what? 255. So starting from all zeros, which is the first number, 0, to all 1s, 255, I can represent, if I look at these 1s and 0s as if they were representing a decimal number, I can represent the numbers 0 through 255. 0 through 255. Or 256 numbers. Remember, 0 is the first number. Now, those 1s and 0s can mean different things. We'll talk about that in a second. So when I talk about patterns of bits, 1 is a bit, 4 is a nibble, 8 is a byte or an octet. We can interpret it as a character. We'll talk about that in a second. 16 is a double byte or a word, because in modern CPUs, we don't just have 8 bits at a time. That would be very slow. We have many more, 64 bits, 128 bits at a time. So we can represent a whole lot of stuff with a binary batch. And when we're looking at these things, especially in Wireshark, we start to see how Wireshark interprets those bytes or those words depending upon what this position in this collection of this stream of bits is supposed to mean for us in that protocol. If we are going to look at those 1s and 0s as a hexadecimal number, hex 16, so 0 through F is 16 different numbers. A pattern of 1s and 0s can be a decimal number, or it could be a hexadecimal number. We could use that pattern of 1s and 0s to represent a character. When I type, what do we got here? When I type a number 6 on my keyboard, what goes down that USB wire? 00110110. A pattern of 1s and 0s, which is interpreted by the word processor as, oh, he typed a 6. Let me put that on the screen. This is why A+ information is important. So you understand what's going on in this path. When I type a letter P, that would have a hexadecimal equivalent of 50, or binary 01010000. A pattern of 01010000 goes down. When I press that P, I'm going to press that P right here, P. So in order for that to appear, 01010000 went down that wire, was interpreted inside this CPU, and by this Microsoft PowerPoint, I'm going to type another P. Another 01010000 went down that wire. I'm going to type a O. So that was 01001111 went down the wire. So what that pattern means depends upon what we're doing. When I have a Ethernet network connection, we're talking about an electronic signal, an electrical signal. It's either high or it's low, which represents a 1 or a 0, 5 volts, 0 volts. Anything over 3 volts typically is interpreted as a 1. Anything under 3 volts typically interpreted as a 0, which is in part why we can get in trouble when the electrical stuff is not working quite right. But that's another whole consideration that comes with more deep A+ learning. So layer 1. If my layer 2 is Ethernet encoding and decoding, and my layer 1 is an Ethernet wire, this is what's going down that wire. Layer 2 turned the 1 and 0 coming down the OSI model. It says, okay, they want me to send a 1, so I need to send this kind of signal out the wire. Well, the information that is going to be encoded, the information that comes from the upper layers and is encapsulated when we get down to layer 2, we have to put that in a package. And in the case of Ethernet, if we're using that as our connection medium, this is how things are defined. We're going to have a preamble, which is like, it's the headlights coming down the road. Something's coming down the road. Let's synchronize with this. Right? We've got a clock signal that I'm using. Data comes in. I synchronize with that, and I interpret that. And then here's the frame delimiter. Okay, here's the beginning of the information. And then here's the Ethernet address, destination. Here's the source Ethernet address. And then here's the length of this. And then comes the actual data. And then at the end, a frame check sequence. So that's the packaging at layer 2. When we look at that in Wireshark, we don't see the 1s and 0s. Wireshark has already interpreted those 1s and 0s to mean either at this point in this data stream, this set of 1s and 0s is supposed to represent this hexadecimal destination Ethernet address. And then let's open up Wireshark here and look at something. So here's Wireshark looking at a PCAP file. Now, do you notice that there's a 0 up here and then 15, 16, 31? What does that represent? Well, that's the bit position of the 1s and 0s coming in. So I've got up to 32 bits, another 64, etc. So this batch of bits, and both Wireshark and the code in your network interface card understand that when I look at this data stream, right, I look at the first 62 bits to synchronize with that, then I recognize the beginning of the information itself, and then I understand at that offset from the beginning of stuff that started to come in, this 48 bits is going to be the destination Ethernet address. Wireshark shows that to us in human readable form. If I was to look at that in terms of hexadecimal, this is where that is. This representation of the bytes, this is the offset 0010, offset from the beginning of the information stream here, having unpackaged the delimiter and the preamble. If there was an ASCII equivalent to this particular, in other words, if this hexadecimal or bit pattern number meant something in ASCII, I would see it over here. But this is actually interpreted as what? We interpret this, we utilize this as hexadecimal. So we interpret that bit pattern, those 1s and 0s, as hex. Interpret this as hex. We interpret this as a IPv4 type. This bit pattern tells us we're carrying IPv4 inside this Ethernet frame. Now the IP header, again, here's the first bit, here's the third bit, 0, 1, 2, 3, 4. Those first 4 bits tell us what version of IP this is. And the programming of our systems understands at this location in the data stream, these 4 bits will tell me what version this is. And then what is that IP header length? And then is there a type of service information here? What is the total length of this header? Then is this a fragment? In other words, sometimes the data stream gets split up and then we have fragments and we have to know where this fragment's going to fit. What's the offset going to be where we start this new information to put it together? What's the fragment offset? What's the time to live? At this location in the data stream, these 8 bits tell us what's the time to live for this. At this location in the data stream, the next 8 bits tell us what protocol we're carrying inside this IP. Then what's our checksum for the header? If we calculate this again after we receive it and get the same number, then we know no bits got flipped in the transmission. At this offset in this data stream, these next 32 bits are going to be what? We're going to look at them and we'll interpret them as a decimal number that's our source IP address, like 192.168.0.10. At this offset in the data stream, this far from the beginning of this header data stream here, these 1s and 0s here, these 32 1s and 0s represent our destination IP decimal address. At this offset in the data stream, these pieces of information here represent options in our IP negotiation here, in our IP operation here. And then we're going to pad this out to be an even length here, and that's our IP header. When I look with Wireshark here, yes, the first 4 bits tell us that's the version number. The header length. Do we have any differentiated services? What's the total length? What's the ID of this particular packet? Remember, we match up IDs, like for a request and a reply for domain name services. We can match up that ID. What about flags? Is there a fragment offset? No, this is not a fragment with an offset. Time to live is 128. We're carrying TCP inside this IP packet, and the checksum for this information here. And what's our source IP address? In this case, what? Those bits there, those 32 bits, represent 24.6.169.43. We're interpreting those as a decimal number. And then we're going to interpret the next 32 1s and 0s as another decimal number that's our destination address. So again, this long data stream, these 1s and 0s mean different things at different locations in that data stream. And at each layer of the OSI model, the programming for whatever portion of our process, or whichever process is at that layer, is responsible for interpreting those 1s and 0s, knows that at this offset, those 4 bits tell me the version number. At this offset, the next 32 bits tell me the source address, so I interpret that. I interpret those 1s and 0s as a decimal number. We interpret that that data stream, the 1s and 0s. Now, TCP, well, this next section of the data stream is our TCP. And the first 16 bits we interpret as our source port, destination port, sequence number for that packet, acknowledgement number for that packet. Header length, reserved bits. Remember, we've got our flags, our SYN flag, our FIN flag, our push, our ACK, our reset flags. At this location in that data stream, this offset from the beginning of the TCP section, that's what the meaning of these 1s and 0s are. Next 16 set of ones and zeros indicates our window size. Then we got a checksum is our urgent pointer, other options and padding. What's our maximum segment size? At a certain offset here, the ones and zeros at that offset would represent our maximum segment size, MSS. Let's go to TCP. TCP options. Well, let's see. Here's a SYN packet. So we know typically, let me go back from this to this. So here's our TCP, here's our options. Let's expand this and see. So at one offset in this set of ones and zeros at this offset from the beginning of the TCP section, what that means, we interpret that as a decimal value. That is our maximum segment value. We know the maximum segment value will be whatever the decimal value of those bits are at that offset in the data stream. Window scale. Are we scaling? Yes or no? Do we permit selective acknowledgements? At this offset in the data stream, the TCP programming interprets those ones and zeros as a yes or no. We do SAC yes, we do SAC no. Again, they're all ones and zeros, but whether we're interpreting as, well, it's a yes or it's a no, or it's a decimal number, or it's a hexadecimal number, or it is an ASCII number, somebody typed a P, or somebody typed an L, or somebody typed a W, depends upon the programming at that level of the OSI model. Wireshark understands how all these protocols work and at what point in the data stream this group of ones and zeros represents a data field and what that field is supposed to represent, what the name of it is, and what the information is supposed to look like when we interpret those ones and zeros and presents it to us in this much more readable form than a stream of ones and zeros going by. Now, if this was UDP, we know that UDP is much simpler than TCP at layer 4, that there's a source port and a destination port and a length and a checksum and then some data, but we don't have acknowledgement numbers and sequence numbers and all that, and the window size and stuff. UDP is just like, yeah, here's some stuff, you get it or you don't, I don't care. But again, if we're using UDP, remember earlier in our packaging, we were told at the IP layer, what am I carrying inside here? Am I carrying TCP? Am I carrying UDP? Am I carrying something else? So now the person at the next layer interpreting that knows, oh, that's TCP, so I should be looking at this offset and what that will mean is a sequence number. If previously you said, what am I carrying? I'm carrying UDP, so at layer 4, the code now says, oh, that's UDP inside, which means that my plan for decoding says at this point in the offset, that's going to be a source port. And then the next bits, right, from 17 to 32, that's going to be my destination port, etc. At each layer, we have information about what's inside. What's inside here? And now the next layer up knows what I'm supposed to use as a plan for interpreting the ones and zeros at each offset in that data stream. It's another way of looking at the TCP header. So what's the bit position? What is the offset in terms of an octet, right? A byte, 8 bits, or an octet. And if I've been told, I'm layer 4, I've been told by layer 3 is sending me a data stream that's actually TCP. I know, okay, let me use my TCP chart here, and I will say, oh, right, from this bit to that bit, that's my source port. And then the next batch is my destination port. I want to look for the acknowledgement number so I know where to go in the offset, and then that 32 bits is my acknowledgement number, x64 actually. And then where's my window size? Okay, I know where to go. The start at this particular point is my window size. I read this much and then I interpret that as a window size. And like that, that's the way it works. So when we're talking about IP addressing, which was kind of the point of this video in the first place, at this offset, the next 32 bits are going to be the source IP address, and when I see them from Wireshark, Wireshark will have separated them out into the 4 bytes or 4 octets and represented that as decimal numbers with a dot in between to indicate that this is this byte, this is this byte, this is this byte, this is this byte, or octet. And the numbers there are 192.168.10.0. And in Cisco, when we're learning CCNA, we actually have to learn to look at those ones and zeros and actually turn them into decimal very quickly in order to complete our CCNA exam. We don't need to do that for Wireshark. Wireshark does that for us. But when we understand what's going on there, that over here in the right-hand octet, there's a 0 in 1's place, so there's no 1's. There's a 1 in 2's place, so that's a 2. There's a 0 in 4's place, so that's a 0. There's a 1 in 8's place, so that's an 8. And then the rest are zeros in 16, 32, 64, and 128's place. So the total decimal equivalent of this pattern of ones and zeros is a decimal 10. And the same thing over here. It's another decimal 10. I got a 2, I got an 8. Don't have anything else. It's a 10. Over here, I've got an 8. I've got a 32, and I've got 128. And that adds up to be 168. Over here, I don't have anything. No zeros, no 1s, no 2s, no 4s, no 8s, no 16s, no 32s. But I got a 64 and 128, which is 192. Well, that's all done behind the scenes for us. But now we understand what's going on in the background, and we understand that these 4 octets at this offset in this data stream are interpreted to mean these decimal numbers, which is our Internet Protocol address. So those 4 octets, the terminology we typically use for IP addressing, represent those numbers. And then that's that 32-bit portion of the entire data stream. That offset represents that address. Now I'm going to play for you a short Cisco IP addressing video, which I'm including in here, which talks about the origin of that, how that works. What about IP addressing? What is a local area network? How do we define a set of addressing for that network? And those numbers, remember, could be 0, could be up to 255 if they've got all ones in an octet. Are there special numbers in there? What about the all 0? What is a network field? What are the network numbers? What are the host numbers? The set of IPs we can give away with DHCP to the devices that are in this local area network here. My printer, my computer, my Roku, my toaster. I can actually give an IP address to my washing machine. It's getting ridiculous, isn't it? But there you go. I could have a conversation.
All devices on an IPv4 network need a 32-bit logical address in order to communicate. This 32-bit logical IPv4 host address consists of a network portion or network ID on the left and a host portion or host ID on the right. The length of these depends on the size of the network. Larger networks will have a longer host portion. A network can be thought of as a range of addresses. All devices on the same network have the same bit pattern for their network ID, but they will have a different host ID. Some addresses in this range are reserved and have a special name and meaning. For example, the first address in the range is used to identify the network itself and cannot be assigned to any host. It is referred to as the network address. The last in the range is called the broadcast address and is used to send a message to all devices on the network at once. It also cannot be assigned to any host. All the IP addresses between the network and the broadcast addresses make up the usable or valid host range and can be used to address the hosts on the network. Let's take a look at how these addresses are determined. In order to forward data, a device needs to know what network it's on. Using their host IP address, their subnet mask, and a process called binary ANDing, a device can find what's referred to as the network address. This address represents the network to which the host belongs and will be slightly different than its host IP. To do this, the device compares their host IP and their subnet mask bit for bit. If the bit values are both a binary 1, the result is a binary 1. If one or both of the bit values is 0, the result is a binary 0. Let's take a look at an example. Let's say we have a PC with a host IP address and a subnet mask of 192.168.2.38/24, and we'll use ANDing to find the network address of the host. Here's the host IP in binary. Here's the subnet mask in binary. If we compare them bit for bit, we can see that a 1 and a 1 results in a 1 and a 1 results in a 1, a 0 and a 1 results in a 0 and a 1 results in a 0, and so on until we have compared all 32 bits. Notice that the last octet is all binary zeros. Because we are using a /24 subnet mask, the first 3 octets represent the network portion and the last octet is the host portion. Network addresses will always have binary zeros in their entire host portion, however long it is. In this case, the last 8 bits. If we convert to dotted decimal, we can see that this host belongs to the network 192.168.2.0/24. Now let's determine the broadcast address for this network, which is used to send a message to all devices on the network at once. Whereas the network address had all binary zeros in the host portion, the broadcast address will have all binary 1s. Since the host portion in this example is just the last octet, to determine the broadcast address, we keep the network portion the same and change the host portion to all binary 1s. This results in a broadcast address of 192.168.2.255. Next, we'll determine the usable host addresses, which lie between the network and the broadcast addresses. The first usable host in binary will be all binary zeros with a binary 1 at the end of the host portion. Converting to dotted decimal, this tells us the first usable host on this network is 192.168.2.1. Lastly, we'll determine the last usable host, which will be all binary 1s with a 0 at the end, the opposite bit pattern of the first usable host. Converting to dotted decimal, we get 192.168.2.254. Let's recap our calculations. We began with the host IP address of 192.168.2.38/24. Using binary ANDing, we determined that this host belongs to the network 192.168.2.0. Keeping the network portion the same, but placing all binary 1s in the host portion, we determined that the broadcast address for this network is 192.168.2.255. Again, keeping the network portion the same but changing the host portion, we determined that the usable host range for assigning addresses to devices on this network is 192.168.2.1, which is one number up from the network address, and 192.168.2.254, which is one number down from the broadcast address. You can see that our original host IP address falls within this range. Things to keep in mind when working with IPv4 addresses. All IPv4 host addresses are 32 bits in length. A portion of the address represents the network that the host belongs to, and that starts at the left. The remaining part is the host portion, which identifies the host on the network. And there are two special reserved addresses on every network that can't be assigned to hosts. One is the network address, which is the lowest in the range of addresses and represents the network that all the devices belong to. And the other is the broadcast address, which is the highest address in the range and can be used for a shout out to all devices on the network at once. Thankfully, there are shortcuts you can take for calculating these addresses without having to convert to binary first. But examining these addresses at the bit level should help you understand how network devices interpret them and also how the dotted decimal format is derived.
So there you go. And then, like that, things to keep in mind. The good news for us who are not doing a Cisco certification right now is you don't really need to be able to do that in your brain, convert from binary to decimal. If you're studying for the CCNA, you need to learn that so that you have that understanding at that level. Although the devices do that for us, now we understand more about what's going on in that background and how DHCP works, because DHCP is what? We've defined a network, we've defined a range. DHCP then gives out IP addresses within that range and keeps track of who has what. And also keeps track of how long they can have that IP address for. Do they need to renew that? Things going on with IP addressing that we see when we take a look at the conversation with Wireshark, which interprets the bit stream for us and interprets it in the way that is needed for the field value at that particular offset. Is it a source port in terms of a number? Is it a sequence number in terms of a number? Is it a flag in terms of a yes or a no? Yes, this is a SYN we're trying to send. No, it's not a congestion window. No, it's not urgent. No, it's not a reset. A 0 is a no in this particular interpretation of this set of bits at this offset in the data stream at the TCP level. So in terms of the operating system, if you are setting up IP manually, you need to know what the default gateway is going to be. Typically it's the lower addresses that are given to the routers. Subnet mask, what IP address we're going to do. If it's automatic, then we've been given that information from DHCP. And that subnet mask is what the devices use to determine, well, what's my network? What network am I on? And then what's my IP? And you saw an example of how the device goes about figuring that out for itself. And then you saw some explanation and usage of the idea of a prefix as, in a sense, it's sort of a shortcut to say, okay, if I want this subnet mask, I want the first 3 octets to be my network, I can just write that by saying /24. And these days, instead of having to write out 255.255.255.0, we can just say 192.168.0.10/24, and the devices interpret that as a 24-bit subnet mask. So those are important things for us to keep in mind from that particular video. And that helps us form a mental picture of things when we see a set of addresses inside a interpretation, well, in this particular one, there's only 2 IP addresses here. Are these on the same subnet? 124 or 24.6.169.43, 24.6.173.220. Well, what's the subnet mask? If it was /24, then what? These two would not be on the same subnet. They would be on different subnets. If it was a /16 or 255.255.0.0, then 24.6 was the network. 24.6 was the network, and they would be on the same subnet. In this particular picture, what? All these guys are on the same /24 subnet. The switch in the middle just forwards those packets based on, what, layer 2. And then the router is going to have an interface that connects to a different network so that we can get off of this local area network and onto something else like the internet. And in the case of this local area network, it is populated with a, what? It's a /24 mask for a 172.16.4 net. And so the available IP addresses would be from what? .1 to .254, because .255 would be the broadcast address that all of these devices would listen to. .0 is the address of the network itself. And in terms of IP addressing, there are 3 sets of addresses that have been set aside to be used for DHCP under RFC 1918, a private address range. So these are not routable on the internet. These are only local area networks, and we need to do network address translation at the router to give me a IP address that's available out in the real world, and keep track of at the router, well, which local area network address is then equivalent to the address that I'm using on the outside, so that data streams can be apportioned properly to my Roku, to my computer, to my laptop, to my iPad, or to my iPhone. All of which, in working here locally in this local area network, have an IP address that's on my local address group. So I might have used a 192.168.0/24 network here. Somebody else down the street could have used 172.16/16. Somebody down the street farther could have used 10.0.0.0/8 as their local area network. And then their ISP, their router, has a real-world IP address, and the ISPs for all 3 of our homes will then forward that information back and forth to the appropriate address. Then the router will forward that internally in our internal network to the appropriate device. Network address translation. What is your IP in the real world? Well, if I run ifconfig here for my Mac I'm using here, I see that my local area network address is 192.168.0.23. Now, the net mask, as it's presented here in the Unix operating system, is written actually as hexadecimal instead of 32-bit decimal. 0xFFFFF.0.0, meaning FF in hexadecimal is the same as 8 ones, 8 ones, 8 ones. So that's 255.255.255.0. And my broadcast address is 192.168.0.255. And then, of course, my router actually here is what, 192.168.0.1. Well, but who am I on the outside of the router in the internet? Well, there's any number of tools for going out to a website which will then tell you what your public address is on the public side of my router. In my case, 75.164.175.77 is my public IP address that my router has on its outside interface. And that's the one given to me by my ISP. Sometimes our company might have actual public IP addresses for things like a public-facing web server. And then on the inside of our firewall, maintain our private IP addresses for our own intranet, and then have another public address that goes out to the internet. So these are called classful addresses: Class A, Class B, Class C, and then there's a Class D block and a Class E for experimental use. In terms of IP version 4 addresses, the Class A network, because it's /8, right? The first 8 bits are the network bits, and there's a total of what? 24 bits available for hosts. So of the total number of IP addresses available with all possible addresses, that Class A constitutes 50% of all the available IP addresses for IP version 4. Class B, the first 2 octets are the network address. The last 2 octets are host addresses, so that comprises 25%, then 12.5 and 12.5 for each of the Class C, D, and E percentage of the total number of IP addresses available under IP version 4. Of course, this is why we went to IP version 6, which we're not going to use very much in this particular class because there's just not enough time. But we need a whole lot more. 128 bits instead of 32 gives us a quadzillion billion addresses, enough to address basically all the atoms that we have. So you pause for a second for you to take a breath and think about all that. This can put things into perspective here, that we've got this data stream coming in, ones and zeros, and at each layer, the code here at Ethernet layer, the code in our internet, in our interface, interprets the ones and zeros at particular positions in that data stream to mean what that field value is supposed to be. And then farther on in the data stream, at a particular offset, the IP level programming code interprets the ones and zeros at that offset to have the meaning that we want for this particular field value. What protocol is inside this IP packet? That's going to tell layer 4 how to interpret the following section of the data stream. The ones and zeros at this data offset position will represent our source port. At this offset position, they will represent our destination port, our sequence number, our acknowledgement number, our flags, our window, our TCP options, and at each offset in that section of the data stream, we'll understand that the ones and zeros are supposed to represent the MSS value, or the window scale, or the yes or no for do we do selective acknowledgements. Now you get more of an idea of how that works. And when you look at a video like the one actually I'm going to do next here, which is interpreting some Nmap scans, you get an idea. You don't have to convert those ones and zeros yourself, but here's what's happening at each layer of the OSI model. At the Ethernet layer, that first section of the data stream is being interpreted. At the next layer of the OSI model, that section of the data stream is being interpreted. And that layer 3 says what's inside. Is it TCP? Is it UDP? So then layer 4 knows, what should I call the information at this location in that data stream? And then inside, same thing. At each layer of the OSI model, that section of the data stream is interpreted by that level of code on up to the application, which interprets that section of the data stream at what you're going to see on your screen. So what's the bottom line? Just to recap a little bit, we've got this stream of ones and zeros, which is what it is all about. All the information is ones and zeros. There's an encoding to those ones and zeros that tells us what they mean, and we understand now that the order of those bits has a meaning in terms of binary ones and zeros being the representation of the powers of 2. And then we interpret those values, those nibbles, those bytes, those words, to mean what we need to know at that offset in the data stream. Whether it's a hexadecimal value, whether it's a character, like I'm typing a P, and then that has a binary value of 01010000 that goes down this wire into the computer and is interpreted by the upper layers as meaning, oh, the ones and zeros at that offset in that particular pattern of that data stream is a P. And this is going to help you when you're looking at all of the representations of the locations, the offsets of this data stream that represent the fields that we're looking for at each layer of the OSI model, and then are interpreted by Wireshark because it knows all these protocols to give you a visual, human-readable interpretation of that data stream of ones and zeros. So that will help you out. And now you have some background. But again, like I said, this is why it is so important to gain all of that A+ level knowledge about what are these devices, how do they work inside, and that gives me the background to interpret it all.